Hello, welcome to Basics of Finite Element Analysis course. Today is the last day of this week, and in today's lecture we will discuss a particular eigenvalue problem and actually develop its finite element formulation and solve it. So, this problem relates to vibrations in a bar, and the governing differential equation of the bar is rho A times partial of u with respect to time minus partial of E A del u del x with respect to x equals q. And to explain, suppose this is the point where which I am considering. U is the displacement in x direction, and it can vary with time and position. This is my x coordinate. Okay. Rho is the density of the bar. In this case, we are assuming that rho is homogeneous, or it is same on that particular small element of the bar. A is the radius of cross section, E is the Young's modulus, and Q is the traction per unit length. It is traction per unit length. So, its units are newtons per meter. So, our goal is to find eigenvalue problems, eigenvalues and eigenvectors using FEA. Okay. Now, our first step is, so this is a second order partial differential equation. It is second order both in time and in space. So, the first thing we do is we try to convert this into a second order ordinary differential equation, and we do that by realizing that if the bar is vibrating like this motion will be, and if it is vibrating on its own, it will have some sort of a harmonic motion with some natural frequency omega, right. So, we say that u of x and t equals a function u x times e j omega t, or excuse me, it is e I omega t. So, this is equation 1, this is equation 2. So, the amplitude of this motion can vary from place to place, but at every point the point will vibrate in a harmonic way, but each point may have a different amplitude, which is u x, but the motion of each point will be harmonic. That is what it means. So, now what I do is put 2 in 1. So, what I get is rho A, and I am going to just write u rather than u x for purposes of brevity. So, rho A u, and because when it is differentiated by time 2 times, so I get minus omega square minus del over del x E A del u over del x and this entire thing E I omega t, right. And because we are interested in finding out the eigenvalues of the problem, the right side of the system will be 0. Now, we note that E I omega t is common to the entire expression. So, I can eliminate this, right. So, I will erase this. The other thing I note, so this entire equation is now only in x, because this capital U is nothing but a function of x only, which means that del over del x equals d over dx, right. So, I will replace these partial differential operators with regular differential operators, total derivative operators. So, it becomes d over dx. So, now I see that I can express this entire expression as E A u prime is equal to rho A u omega square, or I can write it as omega square times rho A u, and there should be a negative sign here. Okay. So, this, if I look at this, it is in the same form as A of u equals lambda B of u, which is the standard form for eigenvalue problem. So, I have developed this, converted this form into an eigenvalue problem statement. Okay. Now, at this stage, I am going to solve these equations using the finite element method, and all of you already know how to solve this problem using the finite element method. The first step in the finite element method, if we want to solve this problem, is we will break the domain into small elements. The second step will be, we will assume an interpolation function for u. We will plug those things here. We will develop and find the residue of the overall thing over the entire element, multiply it by a weight function, equate that residue weighted thing to 0, weaken the differential form, weaken the statement, and develop a system of equations, and then we will solve those equations to get our answer. So, that is the overall process, and that is what we are going to do. So, our overall equation is E A u prime and I will move the negative sign on this side equals omega square, and what I will do is, just for purposes of convenience, I will replace omega square by lambda. So, it is lambda times rho A u. Okay. So, the weak form so now we are going to get the weak form, but before that we will express it as a weighted residual form. So, at this stage, so suppose my bar is this long and this is one, so I have broken it into several elements. This is node 1, node 2, let us say the element is HE. So, for the Eth element, I have length is HE and there are only 2 nodes. So, I am assuming that it is a linear element. But before I get to the element order, I will develop a weighted residual form. So, I integrate it from 0 to HE. I have a weight function W multiplied by minus EA U prime, the entire thing differentiated with respect to x, minus lambda A rho U dx equals 0, dx bar, because I am in local coordinates. From this I develop a weak form So, my weak form is 0 to HE, and I reduce the differentiability on the first term and shift it to W. So, I get W prime, and when I do that, the negative sign before EA goes away, right, minus lambda W A rho U dx bar equals, on the right side I have, so I will get some extra boundary terms and I am shifting them to the right side, and what I get is W evaluated 0 times Q1 E plus W evaluated at 1 no HE times Q2 E, where Q1 E equals minus A U prime evaluated at 0 and Q2 E equals minus A, this entire thing is evaluated, A U prime evaluated at HE. Okay. At this stage, my next thing is that I assume an interpolation function for U. So, U is equal to summation of Uj and phi j x, and this is for the eth element, and j equals 1 to m, and in this case I am using m is equal to 2 because I assume that it is a linear element. Also, my weight function equals phi I for the eth element, which is the variation using principles of variational mechanics. This is nothing but it represents a variation in U. So, then I get 0 to HE d phi I over dx bar EA d phi j over dx bar, all for eth equation, minus lambda A rho, oh here by the way A equals E times capital A. So, coming back to my weak form, this is my first term minus lambda A rho, and W I have assumed as phi I for the eth term, and U will be phi j eth term, and because I have to sum, U is summation of Uj phi j, so I have to multiply it by Uj and sum it up, j is equal to 1 to m, and integrate it over the entire domain. Or because this may not appear on your screen clearly, so I will again j is equal to 1 to m, and I am going to multiply it by Uj E dx bar, okay, and this equals W evaluated 0 Q1 E plus W evaluated HE Q2 E. Now, we look at these two terms, the one in green and the one which is underlined as red. Okay. The green term has EA embedded in it. A is the area of cross section and E is the Young's modulus of the material. And so it represents kind of the stiffness of the system. If you have a stiffer system, E will be high. If you have a very compliant system, E will be less, right. So, this represents stiffness of the system. On the other hand, the red term, the one which is underlined red, if we do not worry about lambda, then it is A times rho times dx is, so suppose you have a small element which is dx long, cross sectional area is A times rho, rho is the density, so it represents mass of the system. Okay. So, what we get is two matrices K minus lambda m, and both these matrices are for the eth element, and this entire thing is multiplied by an unknown vector u, and on the right side I get a q vector, a force vector. But these forces are internal to the system, okay. These are internal to the system. Here Kij for the eth element equals integral of d phi I over dx bar d phi j over dx bar times Ea dx bar. Also the mass matrix, so the stiffness matrix is defined earlier, and the mass matrix is defined as integral of A rho phi I phi j dx bar, and of course everything is with the superscript E. So, that is my stiffness matrix and that is my mass matrix. So, in our earlier problems we had only one matrix which was multiplied by the unknown vector u. Here we have two matrices, one is the stiffness matrix, the other one is the mass matrix, right, and they are, and the mass matrix is multiplied by that lambda which is the eigenvalue of the system, and on the right side you have the q vector which is basically the internal reaction forces at the two ends of the element. Okay. Couple of things. So, this stiffness matrix, if you look at it, it is symmetric, because if you replace j by I and I by j, you get the same answer. So, Kij is equal to Kji. The mass matrix is also symmetric in nature, because when you replace I by j, so Mij is equal to Mji. Okay. So, this is the, so these are the two matrices K and M. So, now at element level we have developed the eigenvalue formulation for the problem. So, our next step is to assemble all these things. Okay. So, that is what we are going to do. So, before I do that, actually I will write down the values of these terms. So, K for the eth element is equal to Ea over He, and this is for the case when M is equal to 2. It is for a linear element. For a quadratic element it will be a 3 by 3 matrix. Okay. For a linear element, it will be a 2 by 2 matrix, and the terms are 1, -1, -1 and 1. And then the mass matrix for the eth element is rho A He over 6, 2, 1, 1, 2. There is one thing interesting you will note at the mass matrix. The overall mass of the system, which is an element He long, will be what? Its cross sectional area times density times He, right. So, you have in mass matrix, at least in this case, the numerator rho A He is the mass, it is divided by 6, and then you look at all the terms in the matrix. You have 2, 2, 1 and 1. If you add them up, 2 plus 2 plus 4 plus 1, 5 and 1, 6, that divided by 6 is, so if you add up all the elements of the mass matrix, they end up with the total mass, and the mass matrix can never be negative, because mass is never negative, it can never be negative. Okay. So, this is something interesting about your mass matrix. So, with this understanding, what we will do is we will develop assembly for our system. So, our system is like this. So, it is a long bar, and at this end of the bar it is rigidly fixed. At the other end of the bar, I have a spring whose stiffness is K. Okay. Now, what I am going to do is, I am going to split this bar into 4 elements. So, this is element number 1, element number 2, element number 3, element number 4. So, I have a total nodes, number of nodes is 1, 2, 3, 4 and 5. Okay. And I am interested in finding out the eigenvalues of this problem. Okay. One thing you will immediately note is that suppose this spring was not there, then the bar would have less problem vibrating back and forth, right. Once the spring is there, then the overall system becomes stiffer. So, bar will have a higher angular frequency, because its overall stiffness, that is K, it goes up, right. So, we have to figure out how to incorporate the influence of this K in the overall assembly level equations, and to do that, first we have to develop the assembly level equations. So, let us write down these assembly level equations. For element 1, our assembly level equation is EA over HE 1 minus 1 minus 1 1 minus lambda rho A HE over 6 2 1 1 2. The entire thing is multiplied by U1 U2 E, and in this case E is, this is the first element. So, E is 1 and this equals Q1 1 Q1 1 2. Okay. So, this is the these are the two equations for the first element. The equations for the second element are identical, except that the superscript 1 becomes 2, okay, because we have assumed that the length of the element is same in all the cases. So, for element 2, EA over HE 1 minus 1 minus 1 1 minus lambda rho A HE over 6 2 1 1 2 this entire thing is multiplied by u1, u2 for the second element, and that equals q vector q1, q2 for the second element. Likewise, I will have another set of equations for element 3, and here it will be the u vector will be u1, u2, 3 equals q1, q2, 3 as the superscript, and for element 4 again similar set of equations u1, u2, 4, 4 equals q1, q2, 4, 4. Okay. So, we have developed 4 sets of element level equations. Total number of equations here is 8, right, and we have 5 nodes, 1, 2, 3 and 4 and 5. We have 5 nodes. So, the first thing we do is we establish the continuity conditions for u. What are those continuity conditions? At node 2, u 2 1 is equal to u 1 2 is equal to u 2. So, this becomes u 2, this becomes u 1. Same using same approach. So, this is u 2. I am replacing all these local degrees of freedom with their global values. This is u 3, this is u 4, this is u 4 and this is u 5. Okay. The second thing I have to note is that the total force at let us say node 2. So, this is continuity and there are three more relations for that, and then the second one is force balance. And for force balance, the total force at node 2 is q22 plus q13, right. Similarly, the total force at node total force at node 4 is q32 plus q14, and the total force at node 2 is sum of these two, right. So, if the total force is that much, then I have to add these equations. So, I have to add this equation with this equation, I have to add these two equations and I have to add these two equations. And then in that way I will get total of 5 equations. Right now I have 8. So, I have 5 equations and I will have 5 degrees of freedom. So, the total number of, so the final set of equations becomes, if I do that, is EA over H naught 1 minus 1 0 0 0 minus 1 2 minus 1 0 0 0 0 0 minus 1 2 minus 1 0 0 minus 1 2 minus 1 0 0 minus 1 1. This is my K matrix, global K matrix, minus lambda rho A He over 6. Then I get global mass matrix. What is the mass matrix? 2 1 0 0 0, 1 4 1 0 0, 0 1 4 1 0 0. So, this is 0 0 1 4 1 0 0 0 1 4. Okay. And this entire thing will be 2. So, this entire thing is multiplied by u1, u2, u3, u4, u5, and this equals the q vector, and the sum of q12, this guy and this guy is 0. So, what I will get is q1 0 0 0 and q5. Okay. Now, let us look at q5. q5 is the force which is being applied on the system due to the spring. So, if the node 5 it moves by a distance u, the spring will apply a force in the opposite direction and its value will be k times u5. So, q5 is equal to minus k times u5. Okay. So, this guy becomes minus k times u5, and because this is unknown u5, I shift this, I move this u5 on the left hand side. So, here what it gets is I get another term here, and this is plus I do not have space to write here. This is negative, and it will be k times h naught by E A, because there is a common term out here. Okay. So, this is coming, this extra term is coming because of this term, and once I have done this, then on the right side this term goes away. So, this entire the q5 the term the constant on the right side in the fifth equation becomes 0. Okay. So, this is the first boundary condition, which is this one. The second boundary condition is that at x is equal to 0, that is at node 1, u is 0. So, I specify this to be 0. Okay. So, now I have to worry only about finding u2, u3, u4 and u5. Okay. Which means, yeah. So, I do not have to worry about my first equation, I do not have to worry about my first equation, because u1 I have to only solve for u2, u3, u4 and u5. So, I have to only worry about the last 4 equations, and also in the last 4 equations when I multiply this minus 1 by u1, it will be 0. So, contribution of these terms will also be 0. So, I will consider only this block in the K matrix, and for the same logic I will consider only this block in the M matrix. So, first I have assembled, now I have reduced the number of equations. So, ultimately what I get is K reduced minus lambda M reduced u2, u3, u4, u5 is equal to 0, 0, 0, 0. Okay. Now, these are 4 equations and 4 unknowns. These equations will be true in 2 situations. Situation 1, case 1, u2 is equal to u3 is equal to u4 is equal to u5 is equal to 0. This is one solution, but we do not like this solution, it is a trivial solution. For this I did not have to do all this finite element analysis. The second solution will be case 2, when the determinant of k reduced minus lambda m reduced equals 0. If this determinant is 0 and I know all the values in k reduced, I know all the values in m reduced, the only thing which I do not know is lambda. That is the only thing I do not know. So, because these are 4 equations, I will get a 4th order algebraic equation in lambda, 4th order equation. So, it will have lambda to the power of 4 times something plus lambda cube times something and so on and so forth. So, I will get 4 values of lambdas. Each of these values is called an eigenvalue, because it is a characteristic of the system, that is what it literally means. Okay. Now, once I get that lambda, so I get 4 lambdas, lambda 1, lambda 2, lambda 3, lambda 4. But what is our goal? We have to find u, right? We have to find u, that was our goal. So, we have found these lambdas. Next what I do is I consider lambda 1 and I plug that lambda 1 in k reduced minus lambda 1 m reduced times this reduced vector u2, u3, u4, u5 equals 0. Now, I know everything in this matrix, I also know lambda 1. So, I can find the relationships between u2, u3, u4 and u5. When I get those relationships, that solution for u is called eigenvector for system corresponding to lambda 1, corresponding to the first eigenvalue. Similarly, I consider the second eigenvalue, so I get a second eigenvector. Then I take the third eigenvalue, I get a third eigenvector. And if the system is having n number of equations, reduced number of equations, then I will get n eigenvalues, n eigenvectors, and each eigenvector will be corresponding to one particular eigenvalues. Okay. So, that is the how I figure out my eigenvectors. Okay. And finally, our original goal was what? To find u. Our original goal was to find u, and we had said that u x t is u x e I omega t, right. So, u x, so in omega we know that lambda equals omega square, that is what we had assumed, right. So, I know what is omega. So, I take first omega 1 corresponding to lambda 1, I put omega 1 in this equation, and I also put u1, which is the first eigenvector. So, that is my first solution. Then I take the second eigenvalue, I find out its eigenvector, put both these eigenvectors and eigenvalue in this solution, and I get the second solution for the system. That is the second solution, and each eigenvector in this case is also called a mode shape of the system. Mode shape of the system means, so you have 4 nodes suppose, 2, 3, 4 and 5. First node does not move because why? Because it is fixed. So what does a mode shape mean? That when the system gets excited by first eigenfrequency, maybe U1 is like this, U3 is this and this. So this is your first mode shape, which means this is the shape or the boundaries between which the system is going to vibrate. Maybe the second mode shape will be this. So it all depends on the system, So you will have 4 different shapes corresponding to 4 different eigenvalues, and the overall solution for each eigenvalue is this. So this completes our treatment for the eigenvalue problem. Next week we will, which will be our final week, we will extend this discussion to 2 important topics. The first topic will be time dependent problems, how do we solve time dependent problems, and the second topic we will cover will be numerical integration, that when we develop all these K matrix relations, how do we numerically integrate them using our computers. So that's pretty much it, and look forward to seeing you tomorrow. Bye.